Hello, aspirant. In the first module, we have seen the application of statistics in various stages of pharmaceutical development, including API development, drug discovery, generic product development, formulation development, clinical trials, bioequivalent studies, etc. Also, we have seen the introduction to design of experiments and quality by design. In the second module, we have seen the various terminologies used in the statistics, and in this current module we are going to see the types of data and also the different types of statistical analysis used in the entire process. Let us go and see the further slides to have the details. Any kind of statistical analysis or any kind of data analysis, the basic requirement is the data. Without data, we can't do any analysis. The data can also be called as variables. So the variables or the data can be classified into quantitative data and categorical data. The quantitative data can be further classified into continuous data and discrete data. What is continuous data? The continuous data can take any value within a range. For example, you have a weight from 40 kg to 80 kg means it can take any value within that range. So that is called continuous measurements, continuous data. Now it come to the discrete data. So the discrete data is nothing but counts and integers. It represents the whole number values, the number of students in class, the number of people in a place, like that. Then it comes to the categorical data. Categorical data first classified into ordinal data. What is ordinal data? For example, a scale indicating no pain, moderate pain and worst pain. So this is called ordinal data. So this is generally used for the endpoint analysis in the clinical trials. This example represents a clinical trial endpoint like no pain, moderate pain and worst pain, which have the scores for each and every terminology what we are using. That is, no pain means 0 and worst pain is 10. Then it comes to the nominal data. It is doesn't have no meaningful order. So this is unordered categories. Example is non-smoker and smokers. If you are classifying the data, non-smoker and smoker, like that, married, unmarried. So this is called nominal data, which comes under the categorical data. So hope we understand the different types of data. What is definition of data? Data is a specific measurement of a variable and it is the value you record in your data sheet. Data is generally divided into two categories which we have already seen in the previous slide, like quantitative data, which represents amounts, then categorical data represents groupings. A variable that contains quantitative data is a quantitative variable and a variable that contains categorical data is a categorical variable. Each of these type of variable can be broken into further type. Data types are an important aspect of statistical analysis which needs to be understood to correctly apply appropriate statistical methods to your data. So we need to understand the type of data what we have in hand before applying appropriate statistical method for the particular statistical analysis. In this slide, we see more about quantitative variables or quantitative data. When you collect quantitative data, the numbers you record represent real amounts that can be added, subtracted, divided, etc. So we already seen there are two types of quantitative variables, that is discrete and continuous. The discrete variables or integer variables are counts of individual items or values. So for example, number of students in a class, number of different tree species in a forest, like that. Continuous variables or a ratio variables is nothing but the measurement of continuous or non-finite values. That is the distance, volume, age, etc. So now we are seeing more into the categorical variable. Categorical variables represent groupings of some kind. So there are sometimes recorded as numbers, but the numbers represent categories rather than the actual amount of things. To understand more, we can see some examples. So these categorical variables further classified into binary, nominal and ordinal variables. What is binary variables or dichotomous variables? So this is generally a questionnaire kind of thing where you have to say yes or no outcomes. So for example, heads and tails in a coin flip, that is called a binary variable. Win or lose in a football game, that is called a binary variable. Or you are asking a question where you have to say yes or no. So that is called binary variable or dichotomous variable. Then what is nominal variable? Groups with no rank or order between them. For example, colors. brands, species names. So these are all comes under nominal variables where you are saying that this many number of brands, this many number of colors, or this many number of species names like that. There is no rank or order between them. Then it comes to the ordinal variables. Here, groups that are ranked in a specific order. For example, finishing place in a race. So all are finishing the line, but you are saying that who has finished first, second, third like that. So that is called ordinal variables. Another example is rating scale responses in a survey. So when you do a survey, you will be giving the rating. So that will be, the rating will be different from different responses. So that is called a ordinal variables. It is ranked in a specific order. We have seen what are data are variables and types of data are variables. Now we are going to see what are the most used statistical analysis methods in the statistical applications in pharmaceutical industry. There are various methods used in to perform data analysis. However, the below are the most used and popular methods in statistical analysis in pharmaceutical development. That is mean, standard deviation, regression, hypothesis testing, sample size determination. We will see each and every statistical analysis method in upcoming slides. What do you mean by mean? This one we have seen in the statistical terminologies also, but here we are going to see how it is being used properly in the statistical analysis. Mean or average mean is one of the most popular methods of statistical analysis. We call it as means procedure. Mean determines the overall trend of the data and is very simple to calculate. Mean is calculated by summing the numbers in the data set together and then dividing it by number of data points. Despite the ease of calculation and its benefits, it's not advisable to resort to mean as the only statistical indicator as it can result in inaccurate decision making. How? That we will see in the upcoming. Standard deviation. Standard deviation is another very widely used statistical tool or method. It analyzes the deviation of different data points from the mean of the entire data set. It determines how data of the data set is spread around the mean. It can use it to decide whether the research outcome can be generalized or not. So we have seen the mean in the earlier slide. You can't take only the mean to decide about a particular test. So here we are seeing the standard deviation. So there is a relationship between the mean and standard deviation, and the standard deviation will indicate how the data is distributed within the data set. If the standard deviation is less, the data is normally distributed and you can take a decision on the particular analysis based on the mean. If the standard deviation is very high, the variation is very high, then you can't generalize the outcome of that analysis based on the mean. So that is what we are telling, that the mean is not only the tool which can be used to take a decision about the statistical analysis, but it is the most widely or wisely used statistical tool to take the outcome of the analysis. However, it is depends on the standard deviation, how much we are getting from the analysis. Regression. Regression is a statistical tool that helps to determine the cause and effect relationship between the variables. It determines the relationship between a dependent and independent variable. It is generally used to predict future trends and events. Regression analysis can be explained by a classical example what we generally do in our laboratory. For example, the UV spectrophotometric analysis. In a UV spectrophotometric analysis, what we do generally construct a standard curve where you will have different concentration and absorption data. So the concentration is plotted in the x-axis, 5, 10, 15, 20, 30 like that. Then you have absorbance, which is measured in the instrument, plotted in the y-axis like this. And you will have the data for example, this against the 5 microgram per ml. For example, you will have the absorption somewhere here. Then you will have another data point here, another data point here, the concentration against the absorption, another data point here, another data point here, like this. So you will have multiple data points which is plotted against the y-axis. So now with this data, if you want to understand the unknown concentration within this standard curve, it is not possible. So that's where the regression analysis comes into the picture. So when you do the regression analysis, then against the data you will have a regressed curve, that is the regression curve, straight line like this. So this straight line will give a equation that is called y is equal to mx plus c. So from which you will have the slope and intercept value. So this slope and intercept value will give, for example, here from the unknown concentration, for example, you have an unknown concentration sample which is showing absorption, for example, here. So then against this absorbance, you can plot and you can identify the concentration of the sample from the regression analysis. So this is the concentration of your unknown samples. Like this, you can do the regression analysis. So this is application of this regression analysis huge in the pharmaceutical data analysis. So when you go actual field work or actual work, you can see a lot of regression analysis, especially in the analytical field of the pharmaceutical development. In this slide, we are going to see about the linear regression. This is the extension of what I explained from the previous slide of the regression analysis. Here you can see the simple linear regression with the data distributed across the regression line. This is also representing a linear regression line with data distributed across and with a error term. And these two graphs showing about linear regression where the data is distributed from bottom to top and from top to bottom. This is called non-linear regression where the data is not related to the variables. That means there is no relationship between the two different variables, that is independent and dependent variable, and it is showing a non-regression analysis where the regression line is not straight. And this graph shows about the formula of what we are getting from the straight line or the linear regression analysis, y is equal to mx plus c, and this is the x-axis, we are seeing the independent variable, y-axis dependent variable. And what is beta 1? Nothing but the c, that is the intercept, and beta 2 is the m, that is nothing but the slope, and they are also called as regression coefficient. E is the error term, and it is the part of y, the regression model, which is unable to explain. So the error term which is not unable to explain, which is called the error term, that is the E. Y is the dependent variable and X is an independent variable. Hypothesis testing. Hypothesis testing can be used to test the validity or trueness of a conclusion or argument against a dataset. The hypothesis is an assumption made at the beginning of the research and can hold or be false based on the analysis results. We have a separate module for hypothesis testing. We will see the hypothesis testing in detail in that particular module. Sample size determination is one of the statistical methodology which is used across various applications, including the clinical trials. And sample size determination or data sampling is a technique used to derive a sample from the entire population, which is representative of the population. This method is used when size of the population is very large, and it can choose from among the various data sampling techniques such as snowball sampling, convenience sampling, and random sampling. We have a separate module on the sample size determination which explains detail about the sample size determination techniques and what is the significance of sample size determination in various statistical analysis, including the clinical trials, bioequivalence, etc. In this slide, we will understand more about sample size determination and how we take a sample from a population. So, for example, we are going to understand a property or understand a characteristic of this particular huge population. So, when we can't take the data collection from all this entire population, huge population, then we are going to select randomly the representative of the population, that is here, this is the sample. So we have to work with this particular sample randomly selected from this huge population. So then we collect the data from this particular selected sample, randomly selected sample, and we do the statistical analysis and we conclude the inference. So the sample data represents the whole population which is we want to analyze. So this is how we need to understand the sample size, how we take the sample from a population. Here we are going to understand the independent and dependent variable. Experiments are usually designed to find out what effect one variable has on another. In our example, the effect of salt addition on a plant growth, we can see. You manipulate the independent variable, the one you think might be the cause, and then measure the dependent variable, the one you think might be the effect, to find out what this effect might be. You will probably also have variables that you hold constant, that is called control variables, in order to focus on your experimental treatment. We will see this with the example. In this slide, we are going to see the dependent, independent, and control variables with the example. So here the type of variable, what is the definition of the variable, and the example is presented. First, we'll see a independent variable or treatment variable. Independent variable is a variable you manipulate in order to affect the outcome of the experiment. For example, you are adding a salt to each plant's water. The amount of salt you are adding is the independent variable to grow a plant. And what is dependent variable? The variable that represent the outcome of the experiment. So any measurement of plant health and growth, in this case plant health is the example. So the amount of salt you are adding into the plant's water, the water you are pouring into the plant, the amount of salt you are adding to the water is the independent variable, and the dependent variable is the effect of this salt addition on the plant's growth with respect to the plant height and wilting. Then what is control variables? The variables that are held constant throughout the experiment. For example, when the plant grows, the amount of light you are exposing to for the plant and the temperature under which the plant is growing, both are called control variables, which are kept in constant, and the volume of water which also you are giving also kept constant. These are control variables, but the amount of salt you are adding in the water is the independent variable, and you are seeing the effect of amount of salt which is added in the growth, which is called the dependent variable. The effect on the growth in terms of the height and wilting, which is called dependent variable. So from this example, you can understand the independent variable, dependent variable, and control variables. This slide talks about the normality of the data. So how we can assess the normality of the data? So there is a normal distribution and how the normal distribution presents, and there is a non-normal distribution, how the non-normal distribution presents. Both we can see in this particular slide. This is the normal distribution and this will be the non-normal distribution. Now we are going to see what is parametric analysis and what is non-parametric analysis. Generally, the statistical test falls into two types, that is parametric test and non-parametric test. So what is parametric test? This parametric test generally assume data follows a particular distribution, that is generally a normal distribution. When there is a non-normal distribution, then we go for a non-parametric analysis. So that is generally usually followed based on the ranks and signs rather than the actual data. In this slide, we are saying the same what we have seen in the earlier slide, but in terms of more explanation about the parametric and non-parametric analysis. So, inferential statistical procedures generally fall into two possible characterization or categorization, that is parametric and non-parametric. Depending on the level of the data plan to examine, a particular statistical approach should be followed. So, the data plan could be nominal, ordinal, or continuous. Depends on that, we have to plan the statistical approach. Parametric tests rely on assumption that the data you are testing resembles a particular distribution, generally a normal distribution with a bell-shaped curve. Non-parametric tests are frequently referred to as distribution-free tests because there are not strict assumptions to check in regards to the distribution of the data. In this slide, we will see more about the parametric test. Parametric tests usually have stricter requirements than non-parametric tests and are able to make stronger inferences from the data. They can only be conducted with data that adheres to the common assumptions of statistical tests. The most common type of parametric tests include regression test, comparison test, and correlation test. Previously, we have seen about the regression analysis. So regression analysis is one of the parametric test, and we know that regression tests look for the cause and effect relationship. They can be used to estimate the effect of one or more continuous variables on another variable. So here we are seeing more about the regression test, which is also one of the type of parametric test. So simple linear regressions contains a predictor variable which is continuous with one predictor. The outcome variable also continuous with one outcome. So generally used in a situation of research question, what is the effect of outcome on the longevity? This we have seen already in the previous slides with the example. Then there is multiple linear regression where it is also continuous with respect to the predictor variable as well as the outcome variable, but there are two or more predictors. However, the outcome will be one. So the research, what is the possible research question would be here is the what is the effect of income and minutes of exercise per day on the longevity. Then there is a logistical regression which is a continuous without a predictor variable, and the outcome can be binary. For example, the research question could be what is the effect of drug dosage on the survival of the test subject. In this slide, we are going to talk about the parametric test which is called comparison test. Comparison tests look for differences among group means. They can be used to the test the effect of categorical variable on the mean value of some other characteristic. T-tests are one of the comparison tests are used when comparing the means of precisely two groups. For example, the average heights of men and women. And other parametric tests like ANOVA or ANCOVA or MANOVA test are used when comparing the means of more than two groups. So generally when there is a two groups, you use the t-test, and when there is a more than two groups, you use ANOVA kind of test. For example, ANOVA is used to analyze the average heights of children, teenagers and adults. Coming to the another kind of parametric test, that is correlation test. Correlation tests check whether the variables are related without hypothesizing a cause and effect relation. These can be used to test whether two variables you want to use in a multiple regression test are autocorrelated. So here you are seeing the Pearson's R with the two continuous variables. The research question could be how are the latitude and temperature are related. So this is a kind of correlation test with a Pearson's R will be evaluated. So the parametric test, the comparison test, when, what, how to use, and how the parity test, independent t-test are used, ANOVA used, that we are going to see in this particular table. For example, parity test will be used when a research question arises. What is the effect of two different test preparation programs on the average exam score for the students from the same class? So the predictor variable is categorical with one predictor. The outcome variable is quantitative and groups come from the same population. So groups come from the same population, which is very important, and where we are going to use the parity test. And independent t-test we are going to use when the groups come from the different populations. Here the question would likely to be what is the difference in average exam scores for students from two different schools. And when you will use ANOVA, the categorical, the data will be the categorical and there will be one or more predictor. The analysis will be quantitative with one outcome, and here there will be more variables, more than one variables. What is the difference in average pain levels among post-surgical patients given three different painkillers? So you are giving three different painkillers to the same population with the post-surgical patients to see the difference in average pain levels. So here you are using three different painkillers. So there are that the variables are more than one. So hence you have to use the ANOVA. Where you use MANOVA, the outcome will be two or more. What is the effect of flower pieces on petal length, petal width and stem length? So here you are going to see the different outcome on the basis of one particular variable. So that is when this kind of data comes, you are going to use the MANOVA. We have already seen what is non-parametric test. So the non-parametric test don't make as many assumptions about the data and are useful when one or more of the common statistical assumptions are violated. However, the inferences that make are not as strong as parametric test. When we don't have many assumptions about the data and we are intent to do a non-parametric test, then in place of these kind of tests like Pearson's or one sample t-test or ANOVA test, MANOVA test, independent t-test, parity test, we can use the non-parametric test for the particular data for which we don't have many assumptions. So that's, for example, there is predictor variables categorical and outcome variables also categorical. Then you can use the chi-square test of independence. Sometimes you wanted to see the quantitative data, groups come from the different populations and the data is categorical, then you can go for Wilcoxon rank sum test. And when groups come from the same population, then you can go for the Wilcoxon signed rank test. So these are all the non-parametric tests you can use instead of the parametric test when you don't have many assumptions about the data. So this Wilcoxon signed rank test and the Wilcoxon rank sum test are generally used in many clinical trials instead of parity tests and independent tests when you wanted to use a non-parametric testings. This slide talks about the difference between the parametric and non-parametric analysis. The key differences are the assumptions. We have the assumptions about the data in parametric, but we don't have any assumption in non-parametric. The central tendency value is around mean value in the parametric, but it is the median value in non-parametric. The correlation in parametric is Pearson. In case of non-parametric is Spearman. Then the population knowledge which is required for the parametric analysis do not required for the non-parametric analysis. And the analysis is used for the interval data, and here in case of non-parametric it is nominal data. The applicability of this test is for the variables in case of parametric. In case of non-parametric, it is attributes as well as the variables. So examples we have seen in the previous slide also, like t-test, etc. for the parametric, and in case of non-parametric, man-Whitney test, Wilcoxon test, all those things comes under the non-parametric analysis. This slide presenting a flowchart for selecting commonly used statistical tests. So whatever we have seen from the slide number 1 to last slide is presented here with a appropriate flow. So it starts with the type of data and assumptions about the data, like whether it is independent, whether it is normally distributed, etc. And also whether the data is continuous or whether the data is discrete or categorical, based on which the further flow of the statistical analysis will be chosen. And when to use the correlation analysis, when to use the regression analysis, and when to use the student t-test, when to use man-Whitney test, so when to use the one-way ANOVA. So all those things are presented based on the data, presentation of the data, how many groups involved. So everything is explained in this particular flowchart, based on which the particular statistical analysis will be selected and the analysis will be carried out for the data. So aspirants, in this module we have seen what is data, what are type of data, and what are the different statistical analysis methods used generally for the statistical analysis, and also what is parametric analysis, what is non-parametric analysis, what is normal distribution of data, what is non-normal distribution of data, what is the regression analysis, etc. We will see another module with a specific topic of hypothesis testing and sample size determination, etc. in the upcoming modules. Thank you.